999 out of 1,000 times, if you have a free body diagram, suppose you draw a labeled free body diagram, and it is out of 5 marks. On your free body diagram, you should be expecting 5 forces. 4 marks, 4 forces, 3 marks, 3 forces. That is the trend. Okay, so let's take a look at this one. 2.2, draw a labeled free body diagram showing all the forces acting on block A while it accelerates to the left. So we haven't even read the question statement, but let me show you something. I can start drawing my free body diagram. What do I mean by that? I know fully well that the weight is gonna be there, so I don't need to read the question in order for me to put the weight on my free body diagram. I can put the weight and think about everything else after, because I know that the weight is going to be there. It's not up for discussion. The earth is going to be pulling the object towards itself. So now let's go ahead and take a look at our question statement so that we can identify all the other forces. Block A of mass 4.1 kg is connected to block B of mass 2.3 kg by a light inextensible string passing over a frictionless pulley. Block A is at rest on a rough horizontal table. So hearing that at rest on a table, normal force, that is the first thing. And we already know from the question that it is accelerating to the left. So if it is accelerating to the left, the frictional force must be to the right. So there we go, we have the frictional force. A and B are connected by a light inextensible string. So we have the tension force. There we go. And then a force F of magnitude 49 newtons is applied on block A. So there we go. Our force F of magnitude 49 newtons. So this is force applied. Let's take a look. 1, 2, 3, 4, 5. 5 marks, 5 forces. I think we are good to go. Let's go ahead and do 2.3. So 2.3.1, we're supposed to calculate the magnitude of the kinetic frictional force acting on block A. So let's go ahead and do that. Quite an easy question. I would assume the frictional force is equals to, well, the kinetic frictional force is equals to the coefficient multiplied by the normal force. The coefficient between the surface of the table and block A is 0.35. So the coefficient is 0.35. All we need is the normal force, and we have answered our question. The normal force in this case is not going to be equals to mass multiplied by gravity because of this force applied. Okay, let me show you. The normal force plus the y component of the force applied. We can resolve the force applied into its components. They're going to be equals to the weight because the object is neither moving up or down. So by saying this, we're saying that the normal is the weight minus the y component of the force applied. So what is the weight? The weight is the mass, 4.1, multiplied by the gravity, which is 9.8, minus the y component of the force applied. The y component is going to be 49. So in a flat surface, cos is x and sine is y. So sine of 50 degrees. So let me get rid of this. I was just showing you how the normal force is coming about. So the frictional force is going to be equals to 0.35 multiplied by 4.1 multiplied by 9.8 minus 49 sine of 50. What do I get? 0.93. So 0.93 newtons. We're only interested in the magnitude, no need for direction. So there we go. That is 2.3.1. But what about 2.3.2? What does the question say? Acceleration of block A. We want to calculate the magnitude of the acceleration of block A by applying Newton's second law to each block separately. I guess people, they don't know that they're supposed to apply Newton's second law to each block separately. You know, the question even states apply Newton's second law to each block separately. I thought we all knew that, but it seems like we didn't. But anyway, stories. Block A, let's apply Newton's second law and see how it goes. So we're going to have F net being equals to ma. Well, the force that is pulling the object minus all the forces that are opposing. That is how I usually say it. So the force that is pulling the object here is the y, not the y, but the x component of the force applied, Fax. So we have Fax minus all the forces that are opposing the motion of the object. So which forces are opposing the motion of the object? The forces pointing in the opposite direction. So in this case is the tension and the frictional force, and this is equals to ma. So Fax, that is going to be 49. We said that x is cos, so cos of 50 minus the tension. I don't think we have the tension. Minus the frictional force. The frictional force is 0.93. This is equals to ma, so 4.1 the mass, and the acceleration is also unknown. Okay, I guess we can solve these and yeah, move to object B. So let's do that. 49 cos of 50 minus 0.93. Am I doing that in the correct order? I think I am. So we get 30.5666 if we round off to 4 decimal places, minus the tension being equals to 4.18. So this is our equation 1. Let's take a look at B. So B, what's happening at B? We have the weight, obviously, and we have the tension force. Am I missing something? Obviously, we don't have the normal, it is hanging. We don't have any frictional force, it's not in contact with F law. So I think there we are. So are we moving at a constant acceleration? No, we are not. But the blocks are moving to the left, so B should be moving up. So the tension, well, let's start by saying F net is equals to ma first. And then the force that is pulling the object is the tension, and the weight is opposing, and this is equals to ma. So what is their tension? The tension is unknown. The weight is 2.3 multiplied by 9.8. This is equals to 2.3a. So tension, what is 2.3 multiplied by 9.8? That is 22.54. So minus 22.54 is equals to 2.3a. So let me, okay, I can make, what do I want to calculate? I want to calculate the acceleration. So I can make the tension the subject of the formula in this equation and then substitute into the first equation. Or I can just add the two equations. But in this case, I think it is easier if I make tension the subject of the formula. So T is going to be equals to 2.3a plus 22.54. Even if you add the two equations, it would still be fine. I think this is the first time I'm actually doing this. Usually I just add the two equations, but it doesn't really matter, right? The math is correct, we know that for sure. So if we substitute these T in equation 1, we get 30.5666 minus the tension, which is 2.3a plus 22.54. This is equals to 4.1a, right? So 30.5666 minus 22.54. This is 8.0266, and it is equals to 4.1 plus 2.3. This is 6.4a. So A is equals to 8.0266 divided by 6.4, and this is equals to 1.25 meters per second squared. There we go. Tell me, which video do you want me to do next? I'm waiting. Use only equations of motion to calculate the value of T1 indicated on the graph. Well, what is happening here? we have a hot air balloon which is moving downwards with a velocity of 3.4 meters per second. Well, a constant velocity of 3.4 meters per second. And what happens is that a ball is dropped with an initial velocity of 0 meters per second, and then it strikes the ground and bounces off the ground. And here, this position time graph is for the motion of the ball. And what we're supposed to do is to calculate the value of t1 indicated on the graph. So t1 would be the time taken for the ball to travel from the instant it is dropped from the hot air balloon until it strikes the ground. So that is t1. So let's take a look at the information we have for that part of the motion. Obviously, vi, even though it is being dropped, it was on a hot air balloon which had a constant velocity. So its velocity will be that of the hot air balloon at 3.4 meters per second downwards. And then acceleration, obviously, now it is in free fall after being dropped. So we're going to have 9.8 meters per second squared downwards. Another information we have is the displacement, delta y, because t1 is when the ball strikes the ground. So there we go, we have delta y. What else do we have? We're interested on the time, so delta t is what we're looking for. So with these four variables, it should be quite obvious what we need to do. Delta y is equals to vi delta t plus I have acceleration delta t squared. I have delta y, I have vi, I have the acceleration. I'm looking for delta t. But as you can see here, we're going to solve a quadratic equation, and I always run away from that for some reason. So let me not use this equation. Instead, I'm going to find vf first, so that I can use vf is equals to vi plus a delta t. Let me show you how. I'm going to say that vf squared is equals to vi squared plus 2a delta y. I'm going to end up using two equations just because I don't want to solve a quadratic equation. But vf squared will be equals to vi, which is minus 3.4. We're taking up as positive. Plus 2, the acceleration is minus 9.8. And the displacement is minus 15. So vf is going to be equals to. So I'm going to put that in my calculator and take square roots at the same time. So plus 2 multiplied by minus 9.8 multiplied by minus 15. I'm getting 17.4803 meters per second. So this is my vf. Now that I have vf, I'm going to say vi is equals to vf, not vi. Vf is equals to vi plus a delta t. So there we go. Vf is minus 17.4803. It is on its way downwards at that instant. And then vi minus 3.4. Acceleration minus 9.8 delta t. So delta t will be equals to minus 17.4803 plus 3.4, everything divided by minus 9.8. So now I just need to put that in my calculator. So minus 17.4803 plus 3.4, everything divided by 9.8. Well, minus 9.8. I'm getting delta t is equals to 1.44 seconds. So there we go. That is the value of t1. T1 is equals to 1.44 seconds. And then the next question, we are interested in the height of the hot air balloon above the ground at the instant where the ball strikes the ground. Okay, let's take a look at that question. So as the ball is moving downwards, the hot air balloon continues to descend, to move downwards, right? Because it was moving downwards initially. So let's take a look at that. We have vi, obviously, which is 3.4. Now we have delta t, because we want the displacement or the height above the ground when the ball strikes the ground, and the ball strikes the ground in 1.44 seconds. So we just need delta y, and then we're going to be able to calculate its height above the ground. So let's see. The acceleration is 0, obviously, constant velocity. So we can say that delta y is equals to vi delta t plus I have acceleration delta t squared. So delta y is what we're interested in. Vi, that is 3.4. Well, let's take up as positive. So VI is minus 3.4, right? And then delta T is 1.44 plus a half. The acceleration is 0, right? Constant velocity. And then the time 1.44 squared. So let me find the delta Y. So minus 3.4 multiplied by 1.44 plus a half. Acceleration is 0. This gives us 0, so let's just forget about that. And what am I getting? Let's see. I'm getting minus 4.896 meters. So there we go. We can move to the next question. Right. Well, we can't. We are interested in the height above the ground. I hope you didn't make that mistake. Right. So the height above the ground will be 15, right? Its initial height above the ground minus the height that it, or the displacement, the distance it has traveled, which is 4.896 meters. So let's see, what is 15 minus 4.896? 10.104. 10.104 meters. So that is the height of the hot air balloon above the ground when the ball strikes the ground. Okay, let's move forward. 3.4. The ball was in contact with the ground for 0.2 seconds and left the ground with a vertical upward velocity of 7.2 meters per second. Use only equations of motion to calculate the value of T3 indicated on the graph. So T3 is the maximum height. It's when the ball reaches its maximum height above the ground after the first bounce. So let's take a look at the information we have. So VI is 7.2 meters per second. This is given to us. But we have VF also because maximum height. Alright? And then acceleration, we know what that is. So we're interested on the time there. So let's find the time. So VF is equals to VI plus A delta T. VF is 0. VI is 7.2 plus acceleration minus 9.8 delta T. So delta T is equals to minus 7.2 divided by minus 9.8. Let me put that in my calculator. Minus 7.2 divided by minus 9.8. 0.73 seconds. Right. But that is not the answer, right? We are looking for T3. Right. So T3 is equals to T1 plus the time between T1 and T2, and then this 0.73. So T3 is going to be, what is the value of T1? 1.44. So 1.44 plus the time it is in contact with the ground, that is 0.2, and then plus finally 0.73. 0.73. So 1.44 plus 0.2 plus 0.73. T3 is equals to 2.37 seconds. Well, here we go. Let's take a look. The first question states the principle of conservation of linear momentum in words. Can you state that for me? Can you state 4.1 for me? The principle of conservation of linear momentum in words. Well, the total linear momentum in an isolated system remains constant. What are we saying? We're saying that the total linear momentum in an isolated system remains constant. The sum of the momentum before a collision or an explosion, not only a collision, right? Because momentum is also conserved in an explosion, as we will see in this question. But anyway, stories, let's go ahead and do 4.2. So 4.2, calculate the distance traveled by trolley B in 1.3 seconds. Quite a unique question in that, for the most part, usually we're supposed to calculate VF, VI, the mass, something like that. But in this question, we're asked to calculate the distance traveled by trolley B in 1.3 seconds. But let's take a look at our question statement and see what is going on. So two trolleys A and B of mass 3.2 kg and 2.6 kg respectively are held at rest on a straight horizontal frictionless track with a compressed spring between them, as shown in the diagram below. So here in front of us, before the spring is released, okay, and then here is after the spring is released. Right, as you can see, after the spring is released, trolley A moves with a velocity of 0.4 meters per second to the left, while trolley B moves with an unknown velocity. That is the information we have. So let's take a look at 4.2. We're supposed to calculate the distance traveled by trolley B in 1.3 seconds. The mark allocation is 5 marks. So 4.1, I had to state the principle of conservation of linear momentum. So my guess is that I'm going to have to use it in 4.2, right? But then the question is a bit tricky. It says calculate the distance. So to some people, it might not be obvious that we still need to use the conservation of linear momentum. But let me show you how we can do that. Well, we know that the sum of momentum before is equals to the sum of momentum after. But what is happening before the explosion? We have two objects and a spring in between. So we can take those masses as one individual mass. But, we don't have to do that. Let's separate the masses. Yeah, because some people will argue that there's a spring in between, so it's not one mass. So let's have M1 V1 plus M2 V2 being equals to M1 V1 plus M2 V2. This is before the explosion, and this is after the explosion. So let's see how we can solve this problem. So before the explosion, we have the two objects that are held at rest. So M1, the mass of trolley A, that is going to be 3.2 multiplied by 0, plus M2, 2.6 multiplied by 0, and after the explosion, not the collision in this special case of ours, the mass conserved 3.2, velocity, let's take direction to the left as to the right is positive, so to the left is negative. So we're going to have minus 0.4 plus 2.6. V2 is what we are interested in. So let's leave that like that. On the left hand side, obviously, this gives us 0. This gives us 0. 0 plus 0. I think it is supposed to be 0. If not what? 0 plus 0 is 0. There's no other alternative. And then on the right hand side, 3.2 multiplied by minus 0.4, that is minus 1.28 plus 2.6 V2. It should be obvious what we need to do in this case. 1.28 is equals to 2.6 V2. We didn't take 1.28 to the left hand side. We added 1.28 to both sides. We cannot take things in math. But anyway, let's carry on. V2, divide both sides by 2.6. Right, so V2 is equals to, what is 1.28 divided by 2.6? That is 0. It is the final answer. No, it's not the final answer. So I cannot round off to 2 decimal places. I have to round off to 4. So this is 0.4923 meters per second. This is the final velocity of trolley B after the spring is extended. But we are interested in the distance. Let's take a look. We have its initial velocity when it starts traveling. We don't have its final velocity because they're not necessarily coming to rest after they've traveled. But our track is frictionless. It's frictionless. Let me show you why I'm emphasizing on that. The forces that are acting on that object is the weight and the normal force. We don't have any force applied. No, we don't have any force applied as it moves. And then we don't have any frictional force. So the acceleration here is 0, right? So the acceleration of the object is 0. We have that. And then we have the time. The time is 1.3. So we have that. We're interested on delta x. So how can we calculate that with these variables? Take a look. Equations of motions, delta x, vi delta t plus a half acceleration delta t squared. Don't ask me if you're going to get the mark if you use d is equals to s multiplied by t. Don't ask me because I don't have the answer. I use equations of motions. I use the equations on the formula sheet. I don't come up with my own equations, so don't ask me. I don't have an answer for that. But if you used this equation, then you're supposed to have delta x is equals to vi. We just calculated it 0.4923 delta t 1.3 plus a half. The acceleration is 0, like we've said. The time is still 1.3, and we square that. This gives us 0, obviously, so we can just concentrate on this. So delta x 0.4923 multiplied by 1.3. Okay, I just substituted the wrong thing in my calculator. Multiply by 1.3. So let's take a look. I'm getting delta x being equals to 0.64 meters. So there we go. That is the distance traveled by trolley B in 1.3 seconds. Right, then 4.3, let's take a look. The average force exerted by the extended spring on each trolley while they were in contact with the spring was 4.2 newtons. Okay, then 4.3, calculate the time it took the spring to extend to its natural length. 3 marks. What an interesting question. It is the first time I actually come across a question like this, and rest assured I've solved a lot of these questions, but I've never came across a question saying I must calculate the natural length of a string. This is, oh well, the time it took for the spring to extend to its natural length. This is the first. But let's take a look at the variables. Right, we have the force that the spring exerts on the two trolleys, and then we're interested on the time. Which other variable do we have? We have the change, well, the impulse, the change in momentum of A and B. We have the change in momentum of those objects. So we have delta P. Then how can we find delta T if we have the force and delta P? We can say that F is equals to the rate in change in momentum. Right, this is Newton's second law in terms of momentum. So now we can see that the force is 4.2. The change in momentum, let's use object A. I'm using object A because I didn't have to calculate the final velocity of object A, right? What if my final velocity for object B is wrong and I use it in 4.3? I don't want to count on positive marking. So to stay on the safe side, I'm going to use object A because the values are given to me. I'm not using my own values. That is wisdom right there. So the mass of object A, that is 3.2. Final velocity is 0.4 and the initial is 0. Right, when the spring is still, what do we call this? When the spring is yet to be released, right, coiled up in a way, and then we divide this by delta T. So delta T should be equals to 3.2 multiplied by 0.4 divided by 4.2. Let me go ahead and put that in my calculator. So 3.2 multiplied by 0.4 divided by 4.2. What's happening? What do I get? 0.3. So there we go. It takes 0.3 seconds for this spring to extend to its natural length. Right, quite a tricky equation. It's not obvious. Yeah, I'm sure it was not obvious to some of the people. Right, 4.4. I must say, examiners are getting more creative. Yeah, the questions we are seeing, they are really cutting edge. Anyway, stories. 4.4, trolley B is now replaced by trolley C, which has a larger mass. Okay, we have replaced trolley B. Let's say trolley C has 5 kgs and see what happens. The same compressed spring is placed between trolleys A and C. The trolleys are then released. The average force exerted by the extended spring on the trolleys remains at 4.2 newtons for the same period of time as calculated above. How does the magnitude of the velocity of trolley C compare to that of trolley B? After the magnitude of the velocity, that is, after the spring has fallen to the track, right? Only greater than, less than, or equal to. So it will be less than. Why am I saying less than? Let me know in the comments. Why is the velocity, the magnitude of velocity of the trolley C with a larger mass going to be less than that of B? I'm interested in your answer for this question. Let me know in the comments. Apart from that, which video do you want me to do next? Here we go. State the principle of conservation of mechanical energy in words. So because we are stating the principle in 5.1, I'm assuming we can use the principle in 5.2. So let's go ahead and take a look. 5.2, use energy principles only to calculate the speed of the crate at point B. So let's go ahead and take a look at our equation statement and see exactly what is going on. So a crate of mass 18 kg initially at rest slides down a frictionless slope from point A to point B. The crate then moves along a rough horizontal surface from point B towards point C. Point A is 3 meters above the horizontal surface. See the diagram below. So that is easy to see. What are we looking for? We're looking for the velocity or the speed of the crate at point B. We're interested at point B. So let's take a look. Here at point B, we have an unknown velocity, but here at point A we have a velocity of 0 meters per second because initially it is at rest. At A we have a height of 3 meters, and then at B our height is 0. So clearly we can use a conservation of mechanical energy here because our slope is frictionless, right? So if we apply that, we will have the mechanical energy at point A being equals to the mechanical energy at point B. The mechanical energy at point A is just the kinetic energy at that point plus the potential energy. And then same is true with the mechanical energy at point B. Kinetic energy plus potential energy. So what is the kinetic energy at point A? We have a half. The mass is 18 kgs, but the velocity is 0 because it is coming from rest. Plus the potential energy. Mass is still 18. Gravitational acceleration 9.8. And then the height is 3. This is equals to a half. The mass is 18 kgs and the velocity is what we're interested in. Plus the potential energy. Mass is 18 kgs, gravitational acceleration 9.8, and then the height is 0 at point B. So this is gonna give us 0, this right here. So we can move to this part. So what is 18 multiplied by 9.8 multiplied by 3? That is 590. Well, 529 and not 90 something. 529.2. And this is equals to 18 over 2. That is 9 v squared. This gives us 0. So let's divide both sides by 9. 529.2 divided by 9. We get v squared is equals to 58.8. So taking square roots on both sides, we get v is equals to 7.67 meters per second. We can leave it like that. Because we are only interested on the magnitude. So there we go. That is the speed at point B. Let's take a look at 5.3. So 5.3, we're supposed to state the work energy theorem in words. So one question and we have two definitions. That is, you're very fortunate if you come across that in the examination. A constant frictional force of 40.6 newtons acts on the crate as it moves from point B to point C, from point B towards point C. The crate comes to rest at point C. Okay. And then we stated the work energy theorem in 5.3. Well, we don't have to talk about that. You guys, you know it by now. And then 5.4, use energy principles only to calculate the distance that the crate traveled from point B to point C. So we need a free body diagram first for the forces acting on our crate from point B to point C. Obviously, we have the normal force resting on the surface, and we have the weight as always. We don't have any force applied, we just have the frictional force. We know that the normal force is not going to do any work perpendicular to the displacement. Same is true with the weight. So, frictional force is the only force that is doing work on the object. So what are we going to have? We're going to have work net being equals to the change in the object's kinetic energy. So work net is just going to be the work done by the frictional force being equals to the final kinetic energy minus the initial kinetic energy. So let's take a look. Work done by the frictional force, it will be Fr multiplied by delta x multiplied by cos of 180 degrees, right? And then this is going to be equals to the final kinetic energy. Well, it comes to rest, so we have 0 minus the initial kinetic energy, half mv squared. The initial at b, right? Because now we are only considering the motion from point B to point C. That is the part of the motion we are considering. So Fr 40.6. So we have 40.6. Delta x is what we're interested in. Cos of 180 is minus 1. So we have minus 1. This is equals to 0 minus a half. The mass is 18 kgs. And the velocity there at point B is 7.67. So we have 7.67 and we square that. So we're going to have minus 40.6 delta x, and that is, let me just drag this down, and that is equals to minus a half. Oh, well, let me just put that in my calculator. I don't have to simplify anything. So let me just do that real quick. I'm getting minus 529.4601. So I'm going to divide both sides by minus 40.6. I'm getting delta x being equals to 13.04 meters. So there we go. That is our delta x, 5.4. What about 5.5? 5.5 is supposed to explain something here. Let's just make sure that we answered what we were supposed to answer in 5.4. Distance that the crate travel from point B to C. Okay, that's fine. So 5.5, the height of the track is now lowered to the height of the track is now lowered so that point A is at a vertical height less than 3 meters. The same crate is again released from point A. How will the distance now traveled by the crate along the horizontal surface before it comes to rest compared to that calculated in 5.4? I think it is going to be smaller than. It is going to be smaller than. Why is it smaller than? It is smaller than because the initial velocity at point B will now be less. If you lower point A, it will now be less. And if that initial velocity is now less, then the distance covered is also going to decrease. That is equation 5. I'm sure we're on the same page. Which video do you want me to do next? Let me know in the comments right now. State the Doppler effect in words. Of course, we're going to skip that. Let's do 6.2. Use the information given to calculate the speed of sound in air. Mark allocation, 5 marks. So let's go ahead and take a look. A stationary listener records the frequency of the sound emitted by the siren of a police car. When the car, which is traveling at a constant velocity, so we have the velocity of the source right away. So Vs is 26 meters per second. Approaches the listener, the recorded frequency is 615 hertz. So the velocity, not the velocity, but the frequency that the listener records, the frequency observed, is 615 hertz. This is when the car it is moving towards. The car passes the listener at t is equals to 1. At time t is equals to 1. Okay, right. And then moves away from the listener. The recorded frequency is now 526 hertz. So this is towards 615. And then when it is moving away, we have fs, not fs, but fl, which is 526 hertz. Use the information given to calculate the speed of sound in air. Okay, not quite sure how we're gonna do this one, but take a look at this. Let's stick to the basics. Let's start with this case where the kite is moving towards. So we're gonna have FL being equals to V plus or minus VL divided by V plus or minus Vs multiplied by Fs. This is the formula as it is before we do any modification. You get a mark for the formula. Now we can modify it. FL is equals to V is the listener stationary, a stationary listener. So the listener is stationary. So we just have V divided by V plus or minus Vs. So we have V, speed of sound in air, of which we're trying to calculate. And then Vs, that of the source. The source is moving towards, right? So we're going to have minus 26 multiplied by the observed, multiplied by Fs. We know FL when the listener, when the sound source is moving towards, it is 615 hertz. So we're going to have that there. So there we go. We have these. We can't proceed anymore because we have two unknown variables. Let's take a look at the case where it is moving away. When it is moving away, the observed frequency, okay, the observed frequency is 526 hertz. And then we have V divided by V. Now that it is moving away, you're going to have plus 26 multiplied by Fs. Fs is all the same because that is the emitted frequency. So we have these two equations. We have this equation 1 and this equation 2. And what we need to do is to solve simultaneously. That's what we need to do. So how can we possibly do that? Well, we have two unknown variables. So it's either we make Fs the subject of the formula in equation 1 and substitute in F2, or we can, what else can you do? We can make V subject of the formula in equation 1 and substitute in equation 2. Whatever we decide to do, it's all going to work out. So let's take a look and see which one is the easier case here. Can we easily make Fs subject of the formula in equation 1? I think so. Let's take a look at what we can do. So with equation 1, we're going to say 615 everything divided by V minus 26. This is equals to Fs. We're just dividing everything by the coefficient of Fs. But we can switch that division into a multiplication, right? If you are dividing by A divided by B is the same as multiplying by B over A. So we can apply that idea to get over that hurdle. So let's go ahead and do that. 615 multiplied by V minus 26 divided by V. We can write it like this instead. And this is Fs. Okay. Let's further simplify it. 615 multiplied by V is 615 V. And then we have 615 multiplied by minus 26. That is minus 15,990 everything divided by V, right? This is Fs. So let's substitute these Fs into our equation 2. Okay. So if we do that, can we take this to the left-hand side first? Can we take that to the left-hand side first? Okay, let's take that to the left-hand side first. If we take that to the left-hand side first, we're going to have 526 multiplied by V plus 26 divided by V. We are applying what we applied on the first equation. Obviously, let's multiply out before we substitute Fs. So 526 multiplied by V is 526V. And then plus 26 multiplied by 526. That is, oh, okay, here we have V. Here we have V. And then plus 13,676 everything divided by v. This is equals to fs. Now, in place of fs, we're gonna then substitute these which we have here, right? So in place of fs, we're gonna substitute 615v minus 15,990, everything divided by v. Think we're getting somewhere. Because we are dividing on the left side by v and dividing on the right side by v, we can just drop v, because the numerators must be equals to each other for those two things to be equals to each other. So right, we're just gonna have 526v plus 13,676 being equals to 615v minus 15,990. I think it's quite simplified now. Let's take these to the left hand side. So 526 minus 615, that is minus 89v being equals to minus 15,990 minus 13,676. That is equals to minus 29,666. So v is equals to, we divide that by minus 89. Let's take a look. I'm getting 333.33 meters per second. That is not a bad value of the speed of sound in air. It is not alarming. If we were getting something like 1,000, we would be very surprised. Or if we're getting something like 200, we would be very surprised. So the math that I applied here, I mean, it is not the only way you can solve this question, right? The concept is the same, but then the math can be completely different depending on which variable you are making the subject of the formula, so on and so on. But essentially, at the end of the day, we should get the same answer. That is 6.2. 6.3, calculate the wavelength of the sound emitted by the police siren. Okay, we want the wavelength of the sound emitted by the police siren. That is out of 4 marks. So the siren emits fs. This is what the siren emits. And then v is 333.33 meters per second. So we have v. We are looking for the wavelength. So v is 333.33 meters per second. Fs, we can calculate it, but at this point we don't have it. So how are we going to calculate Fs? We have this equation here. So we're going to use that equation to calculate Fs. So Fs is equals to 526 multiplied by v is 333.33 plus 26 divided by 333.33. So let me put that in my calculator. 526 multiplied by 333.33 plus 26, everything divided by 333.33. Right. And then when I put that in my calculator, I get 567.0284 hertz. I can actually prove if this is correct, but I don't think it's necessary. I'm quite sure this is correct. Okay, so we have Fs. So now we just need the wavelength. The frequency is equals to the velocity divided by the wavelength. So the wavelength is the velocity divided by the frequency. So let's substitute here. 333.33 divided by 567.0284. Okay, 333.33 divided by 567.0284. This is 0.59 meters. So there we go. We have the frequency. Now 6.4. Sketch the graph of recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and then moved away from the listener. Labeled time t1 on the graph. No values needed to be indicated on the frequency axis. Okay, so let's take a look. First of all, we need the frequency axis. So there we have it, and then we have the time axis. So let's take, what am I doing? Right, so this is the time in seconds, and then this is the frequency in hertz. Have you heard? We don't need to include any values. Okay, so initially, is it moving away? It approaches initially, right? And then after that, it passes and moves away. So when it is approaching, we have a higher frequency. So somewhere here, this is our frequency when we are approaching. And then something happens at T1, right? Something happens at T1s. At T1, it passes the listener and it's now moving away. So we are expecting something like this. The frequency is going to decrease. The frequency is going to decrease. I was supposed to indicate something. Sketch the graph as it moves towards. Okay, I don't know. It doesn't say we must indicate which one is towards. But here, this is towards. As it is moving towards. This is away. And then somewhere in the middle here, we have the emitted. There we go. This is a special question. I did take some time going through it. Let's go ahead and take a look. Calculate the magnitude of the initial charge QB given to ball B if the mass of each ball was 0.012 kilograms. Let's go through our question statement and see what is happening. So two identical neutral balls A and B are suspended from a ceiling by insulated light inextensible strings of equal length as shown in the diagram below. Yeah, we can see our two identical neutral spheres are being suspended there by two strings of equal length. What happens next? Ball B is then given an initial negative charge QB of unknown magnitude. Right, so initially they are neutral and now B is given a negative charge of unknown magnitude. Right, so A still neutral and then B negatively charged. Okay, let's carry on. The two balls attract each other. Obviously, well, it's not obvious to some. So if you have positive and neutral, they attract. But even if you have negative and neutral, they still attract. Neutral attracts with both positive and negative. Right, I did explain that in a separate video, but let's carry on. The two balls are made to touch and then they repel each other. The balls come to rest with their centers 10 centimeters apart so that each string makes an angle of 9 degrees with the vertical. See the diagrams below. Okay, let's see. They touch, get separated, angle of 9 degrees with the vertical. In the first question 7.2.1, we define Coulomb's law, and then in 7.2.2 we're supposed to calculate the magnitude of the initial charge QB given to ball B if the mass of each ball was 0.012 kilograms. Okay, so these spheres, they are at rest at this point when they are 10 centimeters apart from each other. Right, so take a look at this. We have A and B. B has a magnitude of QB initially, right? And then A has a magnitude of 0 because it is initially neutral. And then they are made to touch and separate. When they touch and separate, what is the new charges on sphere A and B? We have Q new being equals to Q1 plus Q2 divided by 2. But the charge of sphere A, we have it is neutral, so that is 0. And then what about sphere B? Sphere B, it is given an initial negative charge QB. So let's write QB there. And then we divide everything by 2. So the new charge on the two spheres, Q new, is equals to QB over 2. So this is the new charge in both spheres A and B after they touch and separate. Okay, and then when they touch and separate, take a look at this. The balls come to rest with the centers 10 centimeters apart from each other. So when they come to rest them, when they're 10 centimeters apart from each other, this is what is happening. So let's focus on sphere A, for instance. This is also going to work if we focus on sphere B. So they have the same magnitude now, so they are repelling each other. So this is the electrostatic force of sphere B on A. And then we have the tension. The tension is what's balancing the force of B on A. So let me not just say the tension, but rather the X component of the tension. So this is what we have. We have FB on A being equals to Tx, the X component of the tension. We can also use sphere B. We'll still get the same answer. So you don't, have to worry about that. Right. So that is the situation we have. And that is what is going to allow us to find our answer. Well, we can add more forces here, because that tension force, that is the X component on A, right? But obviously we also have the Y component, which is Ty. And then on top of the Y component, we have the weight. So this is how we can solve this question. We can say, because we want to find QB, don't forget that we want to calculate the magnitude of the initial charge QB. QB is what we're interested in. So if we take a look at the forces acting along the x-axis, we can say that FB on A is equals to Tx. We can say this because it is said that the balls come to rest. So FB on A is equals to Tx. But what is the electrostatic force? Is K Q1 Q2 divided by R squared. And then here we have Tx. Let's leave that in that way for the time being. So, or we can just write it as T cos of theta or sine of theta. T cos of theta. So that is what we have there. We have T cos of theta. So K, that is 9 times 10 to the power 9. Q1, the magnitude on A, it is QB over 2 after the charge. And then the magnitude on B, it is also QB over 2 after the charge, divided by the distance between them squared. So the distance between them is 10 centimeters, but we use meters in physics. So that is 10 divided by 100. Dividing by 100, 10 centimeters to meters. We square that. That is equals to T cos of theta. So let's take a look at our angle. We have T what? So take a look at this. I'm just gonna put the sketch here. Okay, so here we have an angle of 9 degrees. There we have an angle of 9 degrees. And then obviously we know that here we have 90 degrees. So what is this angle that we're supposed to use? This angle here is going to be 81 degrees. So in order to find the x component of the tension, we're going to say T cos of 81 degrees. That is going to allow us to find the x, because we know fully well that cos of theta is equals to the adjacent over the hypotenuse. So cos of theta is equals to the adjacent is x and the hypotenuse is the tension. This is Tx, by the way. So we have Tx being equals to T cos of theta, as you can clearly see. So this works. Right, let's delete that and carry on. So we have T cos of 81. So on the numerator on the left hand side, we can take, okay, how can we solve that? There's a couple of ways we can use. Well, 9 times 10 to the power 9 is the same as 9 times 10 to the power 9 over 1. So let's just multiply the numerators together and the denominators together. If we multiply the numerators together, QB multiplied by QB is QB squared. So we're going to have 9 times 10 to the power 9 QB squared divided by 2 multiplied by 2 is 4. Everything divided by, so now we are concentrating on the denominator. The denominator is 10 over 100, everything squared. So this is, it is in scientific. Let me see if it looks better in normal. This is 0.01 and it is equals to T cos of 81 degrees. Well, we can further simplify this, obviously. We can further simplify this. But instead of doing that, let's find the tension first and then be able to find QP. Okay, so how are we going to find the tension? Let's go back to our diagram. Ty is equals to the weight. We have the weight, obviously, because it's just the mass of the object multiplied by the gravity. So it will be easy to find Ty. Let me show you. So Ty is equals to the weight. So T should be the weight divided by sine of theta, because Ty is T sine of theta. So T, the weight, what is the mass? 0.012 multiplied by 9.8 divided by sine of theta. So this is sine of 81. This is equals to, so the numerator 0.012 multiplied by 9.8 divided by sine of 81. This is 0.1191. So there we go. We have our tension. So now we can substitute it back here. So let's go ahead and do that. Well, because I can, I just rip through space and time. Let me do that. Let me rip through space and time. Right. So I think I just deleted something I had solved there. Yes, this is what I want to drag down, not everything. This is what I want to drag down. So let me drag these down. Right. So now I have 9 times 10 to the power 9 QB squared divided by 4, everything divided by 0.01 being equals to T. T is 0.1191 and then cos of 81. So let me put the right hand side in the calculator. Alright. So 0.1191 multiplied by cos of 81. My calculator is in degrees. I'm getting 0.0186. And then now let's go back to the what? Let's go back to the left hand side. So in the left hand side, let's change this division to multiplication. How do we do that? We do it in the following way. So we have 9 times 10 to the power 9 QB squared, everything over 4. Let's just take these to the right just a little bit, and then multiplied by, so when you multiply, so initially if you're dividing by A over B, when you change it to multiplication, you just multiply by B over A. So here we had 0.01 over 1, and now we're going to have 1 over 0.01. So there we go. Multiplying the numerator, the terms on the numerator together, we're going to get 9 times 10 to the power 9 QB squared divided by 4 multiplied by 0.01, 0.04. So again, let me pull that down. Okay, so in the denominator I have 0.04. This is equals to 0.0186. Okay, let's cross multiply. We're going to have 9 times 10 to the power 9 QB squared being equals to 0.04 multiplied by 0.0186. That is equals to, let me put my calculator in scientific, 7.44 times 10 to the minus 4. I'm going to divide both sides by 9 times 10 to the power 9. So divided by 9 times 10 to the power 9, I get QB squared being equals to 80.2667 times 10 to the minus 14. Now I take square roots on both sides. So let me go ahead and do that. I get 2.8752 times 10 to the minus 7 columns. So there we go. That is 7.2.2. Give a reason why there is no current through resistor RZ. Let's go ahead and take a look and see why there is no current through resistor RZ. The question statement: a battery of EMF 12 volts and an internal resistance of 0.2 ohms is connected to 3 resistors, a high resistance voltmeter and 2 switches, an ammeter and connecting wires of negligible resistance, as shown in the circuit diagram below. The 3 resistors have different and unknown resistances. Okay, the resistance of Ry is twice that of Rx. Okay, let's see what we can do with that. When both switches are closed, the reading on the ammeter is 5.5 ampere. When S1 and S2 are closed. Okay, then back to our question. Give a reason why there is no current through resistor RZ. So let's see how the current is going to flow. It flows from positive to negative, obviously. So here's our current flowing. It just keeps flowing here at the corner, nothing special, right? And then our current keeps flowing, it keeps flowing. And at this point, when the switch is open, the current divides, right? Because we have 2 paths. So a proportion of the current is going to go down this path, a proportion of the current. And another proportion of the current is going to go down through Ry, okay? And then here, we start having total current once more. But at this point, we have 2 paths. One path is just a piece of wire, and the other one is resistor RZ. But we know fully well that the current want to take a path of least resistance. So because in that path, this path with our switch S1, there is no resistor, all the current is going to pass through S1. No current is going to go through RZ. This is what we call a short circuit. So all the current is going to actually go through our resistor, not our resistor, but through that path with the switch S1, because there is no resistance there. So that is why no current is going to flow through resistor RZ. 8.1. What about 8.2? Calculate the resistance of Ry. 5 marks. Let's see how we can do that. So let me just erase this for the sake of clarity, obviously. So what do we have? Let's take a look. We know that the EMF is 12 volts. The internal resistance is 0.2 ohm. What else do we have? We have the current when both switches are closed, right? IT in that case is 5.5 ampere. What else do we have? Let's take a look. Calculate the resistance of Ry. Okay. We know that Rx, let's say that the resistance of Rx is X. If this is the case, then the resistance of Ry is going to be 2X, because it is said to be twice that of Rx. Okay. And Rx and Ry is what's giving us our external resistance, because no resistance, or well, no current is passing through RZ, so it's not playing a role there. So we can essentially say that, take a look at this. We can say that the EMF is equals to the total current multiplied by the total external resistance plus the internal resistance. We can use that. So we have the EMF, we have the total current, and we have the the internal resistance. How about R external? R external is Rx and Ry, of which those two are in parallel to each other. So Rp is equals to R1 multiplied by R2 divided by R1 plus R2. So R1, let's make that Rx is X multiplied by R2 Ry, which is 2X divided by X plus 2X. X multiplied by 2X, that will be 2X squared divided by 3X. X and X cancels out. We are left with 2X over 3. This is Rp, which is our external resistance. So EMF, we're substituting now into this equation. EMF is 12 volts. The total current is 5.5. And then internal resistance, well, external is 2x over 3 plus internal, which is 0.2. Okay, let's divide both sides by 2.5. So what is 12 divided by 5.5? I mean, what is 12 divided by 5.5? This is 2.1818, 18, being equals to 2x over 3 plus 0.2. So let's minus 2.1818 with 0.2. We get 1.9818 being equals to 2x over 3. Let's cross multiply. When I multiply that by 3, I get 5.9455 being equals to 2x. So divide both sides by 2. 2.97 ohm is equals to x. This is the resistance of Rx. We're looking for the resistance of Ry. So Ry is going to be equals to 2.97 multiplied by 2. So let me multiply that by 2. I'm getting 5.9455 ohm. I should have just left it here because Ry is 2x. But it's fine. I didn't see that at the time. I was just focusing on solving. Okay, but that is fine. We have Ry. Let's do 8.3. 8.3, what are we looking for? Calculate the power dissipated by Rx. So we know that the resistance of X is 2.97 ohms. So in order to calculate power, it's either we need the current or the voltage through X, one between the two. In order to find the current through X, the approach that I take, I would need to find the voltage through X. Well, the potential difference that X causes. So it's better I just calculate the voltage that, the potential difference that Rx causes instead. So how can we do that? Take a look at this. In the external circuit, this is the only part where there is a potential difference, because Rz is not playing any role. So V external is equals to Vp and is equals to Vx, the voltage that caused by, well, the potential difference caused by Rx. So, okay, how can we find V external? Well, we can say that Vx is equals to the total current, which is 5.5 multiplied by the external resistance. The external resistance is 5.9455, which is Ry plus Rx. Well, that is not the right way of doing it because they're in parallel. So we should be using Rp. So it's 2x over 3. X is 2.97, right? So this is Vx. So 5.5 multiplied by 2 multiplied by 2.97 divided by 3. Let's see. Oh, so this is 10.89 volts. So that is the voltage there. So the power dissipated by Rx, we're going to then have P being equals to V multiplied by I. So V is 10.89. And no, let's not use this one because we don't have I. Yeah. So let's use instead P is equals to V squared over R because we do have R. So take a look. V squared 10.89, we square that and we divide by R. R is 2.97. So this is equals to, so let me just substitute that in my calculator. 2.97. I'm getting 39.93 watt. Okay, there we go. That is the power dissipated by resistor X. We are making some progress. 8.4, let's hear the stories. Calculate the reading on the voltmeter. What is happening? When both switches are now open, the reading on the ammeter is 1.3 ampere. So the reading on the voltmeter connected across the battery, the ends of a battery, it reads V external, right? And we know that V external, well, there's two ways of doing it. We can say that EMF is equals to V external plus V internal. Making V external the subject of the formula, we get EMF minus V internal. The EMF is 12, but we can find V internal because we have the current. The current is 1.3 and the internal resistance is 0.2. So we can just use this instead. So 12 minus 1.3 multiplied by 0.2. This is 11.74 volts. So the external resistance has increased. Well, the reading on the voltmeter, the external voltage has increased. But that is expected because the external resistance has increased. But anyway, that is 8.4. What about 8.5? Switch S1 remains open while switch S2 is now closed. So let's take a look. S1 is now open. When S1 is open, there is no current that flows in this direction. So Rx is receiving current. It's now Rz is receiving current. It's now taking part. Switch S1 remains open. So yes, it is passing through Rz. And then switch S2 is now closed. Calculate the reading on the ammeter. Okay, this is 6 marks. So we want the current. Let's see what is happening. We have the EMF, obviously. But do we have R external? We don't have R external anymore. I say that because we don't have the value of RZ. Do we have R internal? We have R internal. So take a look at this. We have two unknowns, the current and R external. But we want the current. So it is our duty to find R external first. R external, we have Rx and Ry. That which we don't have is Rz. So the question is forcing us to find Rz first. How can we find Rz? Well, we have the reading on the ammeter when both switches are open. So essentially, let's take a look at that case. That case will allow us to find Rz. Okay, and then we also have the voltage when the two switches are open. So take a look at this. First, I'm going to say that V external is equals to I multiplied by R external. Let's take a look at what happens when both switches are open. When S2 is open, let me erase this first. When S2 is open, there is no current that flows in this path. And then when S1 is open, current flows through Rz. So when S1 and S2 are open, our external resistance is Ry plus Rz. They are now in series with each other. So V external, which is 11.94, we know that from the previous question, is equals to the current, which is 1.3. Yes, the current is 1.3. Multiplied by R external. R external is Ry plus Rz. Ry is 5.9455. So 5.9455 plus Rz. So this is how we can find Rz. We can divide both sides by 1.3. This is 11.74 and the 0.94 is 74. Let me just substitute this in my calculator once more and verify. 12 minus 1.3 multiplied by 0.2, 11.74. So right, this is 74 and the 0.94, but nothing hectic. 11.74 divided by 1.3, that is 9.0308, being equals to 5.9455 plus Rz. So Rz is going to be 9.0308 minus 5.9455 0.00855. This is equals to 3.0852. So there we go, we have RZ. So now we can work our magic. Switch S1 remains open. So RZ is receiving current. While switch S2 is now closed. So we have those three resistors now taking part. Those three resistors are now taking part. So R external, when the three resistors, all of them are taking part, is going to be, so we have RP plus RS. RP is 2x over 3 plus RS. RS is RZ. So 2, we know that X is, let's check, X is 2.97. So here we have 2.97 divided by 3 plus RZ. RZ is 3.0852. So R external, let me substitute that. 2 multiplied by 2.97 divided by 3 plus 3.0852. Okay, this is 5.0652 ohms. So this is our external resistance. We want to calculate the current. Let's don't forget. So now we can say that EMF is the current R external plus R internal. So the current is going to be the EMF divided by R external plus R internal. Please don't do this in the examination. Don't rearrange the formula, substitute first. Okay, the EMF is 12 as the same. R external is 5.0652 plus internal resistance, which is 0.2. So we have 12 divided by 5.0652 plus 0.2. This is 2.279, 2.28 actually, rounding off to 2 decimal places because we are at the final answer. Does it make sense? Let's see. Yes, it makes sense. I think it makes sense. So there we go. What is the direction of the current in the external circuit? Write either X to Y or Y to X. So let's go ahead and take a look. We have a generator in front of us. It's here in the equation statement. So with the generator, we use the right hand rule, and then with the motor, we use the left hand rule. So let's go ahead and apply the right hand rule on this generator and see whether the direction of the current is going to be X to Y or Y to X. So let's take a look. We are placing our hand right here on this part of our coil. So it's your right hand. Your thumb, your index, and your middle finger are at right angles to each other, right? And then with your index finger, you point from north to south. And then now comes the direction of your thumb. Your thumb has to follow the force of the direction in which the coil is moving. The coil is moving clockwise, as you can clearly see here from our sketch. So this part that you're interested on is going to be moving upwards if the coil is moving clockwise. So there we go. That is going to be the direction of the thumb. So if you place your index from north to south and your thumb is pointing upwards, then your middle finger is going to point in that direction. So that is the direction of the current. So take a look at how the current flows in this manner. And as you can see, when we get to our external circuit, it is flowing from Y to X. So the answer to 9.1, we have Y to X. And then 9.2, say the energy conversion that takes place in this generator. So in a generator, we convert mechanical energy to electrical energy. We have mechanical to electrical energy, right? That is 9.2. And then in 9.3, The maximum voltage produced by the generator is 125 volts. Now the first question, determine the term root mean square voltage. Well, this is a definition that most people get wrong, right? Because it is oftenly overlooked. People, they don't really practice this definition. So I wonder if you actually know this definition. Can you just state it for me in the comment section? Just put in the keywords there. I want to see something. A lot of people think that they know these definitions, but they don't. So that is 9.3. 9.4, calculate the root mean square voltage of this generator. So we are looking for VRMS. We know that it is Vmax divided by square root of 2. I think we all get this one. And then if we substitute Vmax, 125 divided by square root of 2. So let me take a look. 125 divided by square root of 2. I'm getting 88.39 volts. So that is the root mean square voltage. While on the other hand, the 9.5, the total resistance is said to be 42.4 ohms in the external circuit. The question, calculate the maximum current induced. So if we want to find the maximum current, we know that I is equals to V over R. But I max itself, the maximum current, will be V max divided by square root of 2. So let's take a look. Do we have V max? Yes, we do. 125. And then not square root of 2 here. I'm making a mistake. The resistance, what's happening? Divided by the resistance, not square root of 2. The resistance is 42.4. So 125 divided by 42.4. This is 2.95 ampere. And there we go. That is our maximum current induced. 9.6, the last question. Oh, well, this is not that long. 9.6, the generator induced the current at a frequency of 20 Hz. So we have F being equals to 20 Hz. The coil started rotating from the initial position. Okay, as shown in the diagram above. Sketch a graph of induced current versus time for 2 complete rotations of the coil. Okay, let's see. Induced current versus time. What are we supposed to indicate? We're supposed to indicate the time taken for the 2 rotations and the maximum current induced by the generator. Okay, so the position that we have on the sketch, is that going to give us a current of 0, the initial position, or the maximum current at t is equals to 0? That is what we need to figure out first. So here we have current in ampere. So this position that we have in our sketch is where we have our maximum current. So it means that our graph should start from up here. That's where our graph will start, because the position in the sketch gives us the maximum current. So we need 2 complete rotations. So, well, I'm not starting off in a manner that I like there. So this is 1 complete wavelength, and I will have to extend my line here. So let me erase this and extend my line. Well, I can draw the line after, it's fine. But that is 1 complete rotation. And then now we have the second one. So let me just put that line there and see if what I'm saying is correct. So from here to here is 1 wavelength. Then from here to here is another wavelength. Okay, what I'm doing is correct. So there we go. We have our 2 rotations. This is the time in seconds. We need to indicate a couple of things: time taken for the 2 rotations and the maximum current. Let's start with the maximum current, 2.95. Now let's come to the time. We're given the frequency, which is 20 Hz, but we know that with the frequency we can find the period. So what is 1 over 20? 1 over 20 is equals to 0.05. So the time taken to complete the 2 rotations will be 0.05 multiplied by 2, because the period is for 1 complete cycle. So if you multiply by 2, we get 0.1. So here we have 0.05 and there we have 0.1. So there we go. That is question 9, electrodynamics. We all know how to define the term photoelectric effect at this point. So let's just go ahead and do 10.2. Let's take a look at the question statement. Light of a wavelength 4.7 times 10 to the power 7 is shone onto the surface of a piece of metal. If the threshold of the metal is 4.37 times 10 to the power 14 Hz, calculate the maximum speed of an electron ejection from the surface of the metal. So let's take a look. We have the wavelength, right, of the light that is shown. And then we have the threshold frequency of the metal. And then we are looking for the maximum speed. We are looking for V max. This is what we are interested in. So how can we possibly combine all these formulas with all these variables, with one equation and solve for V max? Well, we know that E is equals to H plus constant multiplied by the frequency, right? But if you don't have the frequency and you have the wavelength, you can just use the C divided by wavelength, right? C being the speed of light. So that is the energy, right? And then apart from that, we also have the energy being equals to the work function plus EK max. Well, the work function is just H multiplied by the threshold frequency plus EK max. EK max is a half mv squared. Well, not just any V, but V max, of which we are interested in. So the energy is equals to this equation, and the energy is also equals to this equation. So we can equate the two equations, as you can clearly see. We can say that Planck's constant, speed of light divided by wavelength, is equals to Planck's constant, threshold frequency, plus a half the mass V max squared. Right, we can do this because all these equations are equals to the energy. So now we can go ahead and calculate Planck's constant, that is 6.63 times 10 to the minus 34, multiplied by the speed of light, which is 3 times 10 to the power 8, divided by the wavelength. The wavelength is 4.7 times 10 to the minus 7 meters. This is equals to Planck's constant once more, 6.63 times 10 to the minus 34. Then the threshold frequency, we have 4.37 times 10 to the power 14 Hz, plus the maximum kinetic energy. So let's add it here, plus a half. The mass is the maximum speed of an electron that we're interested in. So the mass is going to be 9.1. Is it 9.1 or is it 9.11? Let's verify. 9.11 times 10 to the minus 31, right? So 9.11 times 10 to the minus 31 multiplied by V max squared. So we are done with the physics. Essentially, we just need to solve for V max squared. So let's put these, what is on the left hand side, in the calculator first. So 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the power 8 divided by 4.7 times 10 to the minus 7. Okay, so on the left hand side I have 4.2511 times 10 to the minus 19. This is equals to, so now let's substitute these in the calculator. 6.63 times 10 to the minus 34 multiplied by 4.37 times 10 to the power 14. Yes, I'm just verifying to see if I'm substituting the right thing. So this is 2.8973 times 10 to the minus 19. And then we have a half multiplied by the mass of an electron. So it is just 9.11 divided by 2. So we get plus 4.555 V max squared. So let's take these to the left hand side. So 4.2511 minus 2.8973 is equals to 1.3538 times 10 to the minus 19. This is equals to 4.555 V max squared. So we can divide both sides by 4.555. Okay, I see the mistake I'm doing here. Right, I was surprised. This is 4.555 times 10 to the minus 31 V max squared. Right, so this is 4.555 times 10 to the minus 31 V max squared. So we are dividing both sides by 4.555 times 10 to the minus 31. So 1.3538 divided by, well, times 10 to the minus 19 divided by 4.555 times 10 to the minus 31. Let's see. 2.9721 times 10 to the power 11 is equals to V max squared. Let's take square roots on both sides. Let me convert it to scientific. I was getting a big number there. I'm getting 5.45 times 10 to the power 5 meters per second being equals to V max. So there we go. That is the maximum speed of an electron ejected from the surface. Okay, let's take a look at 10.3. 10.3. A simple electroscope consists of a zinc disc, a metal stem, and a thin length of gold foil. Right, a gold foil. When the electroscope is neutral, the foil hangs vertically as shown in diagram 1. Vertically, as we can clearly see here, it's hanging vertically, right, straight downwards. Okay, let's hear the stories. When the electroscope is negatively charged, the foil is repelled from the stem, as shown in diagram 2. So when it is negatively charged, it gets repelled a bit. Okay, let's hear the stories. When ultraviolet light is shown on the disc of the negatively charged zinc electroscope, the foil collapses towards the stem, hangs vertically. So when we have ultraviolet that is shown here, the foil starts to hang vertically. We're going to talk about why that is so in a few. First question, 10.3.1. How does the frequency of the ultraviolet light compare to the threshold frequency of zinc? Right, only higher than, lower than, or equal to? It is higher than. That is why the photoelectric effect is taking place. The question says, explain why the foil of the electroscope collapses. So, okay, let's take a look. When it is negatively charged, the foil, it gets repelled, right? And then we are told that when ultraviolet light is shown, the foil falls back. The foil is falling back because now it is neutral again. We know that when it is neutral, the foil hangs vertically. So why is it neutral from being negatively charged, right? It was negatively charged and now it is neutral. Why is that the case? It was negatively charged and now it is neutral. Why is it the case? That is because light of suitable frequency has been shown and then an electron has been ejected, right? So that is how we know that ultraviolet light has a frequency that is higher than the threshold because an electron or electrons have been ejected. That is why it is no longer negatively charged and now it is neutral and the foil is falling back. Right. And then 10.3.3, green light is now shown on another negatively charged zinc electroscope. The foil does not collapse. Will the foil collapse if the intensity of the green light is increased? Right? Either yes or no. Give a reason for your answer. So the question is no. Oh, well, the answer is no, not the question. The answer is no. Why? If green light is not making the foil to collapse, it means that the green light is not of suitable frequency. The frequency is not high enough to eject the electrons. So if you increase the intensity, but the frequency is less than the threshold frequency, electrons are still not going to get emitted because there isn't enough energy to eject the electrons. So it doesn't matter what you do with the intensity. If the frequency is less than the threshold, no electrons are going to be emitted. So that is why the answer is no.